Okay, and so that's supposed to say recording in progress. Up until now, we have worked with regression. We have worked with scatter plots, right? I got you to take some data, plot a bunch of points, and do a line of best fit. Right? We've done it before, whether we called it a scatter plot or whether we called it a special word called regressions or not. I know you've seen it before. So visually, it shouldn't be anything new, but what I'm going to do with it today might be slightly new. As a reminder, this unit is still part of data analysis. So assuming that you're comfortable, assuming that you are comfortable with box and whisker, assuming you understand that we're taking a bunch of numbers from a table of values and doing something with it, today won't be too big of a deal. There's only a couple of things that's new today. And from there, we're going to learn how to get all of that done on desmos.com. So even if you don't quite understand the math, I need you to be comfortable with the technology you can use to help you. With me so far? Everyone's good? So here's some of the new parts. First, I need to make sure you understand the lingo. And that is, does this look like a linear or non-linear relationship? And trick question, there is an example here where there is no relationship. Okay, so let's take a look at these models, look at these examples, and we'll talk. Example number 1 on the left side. If this was my scatter plot and I asked you to identify a relationship between x and y, in other words, age and height, would you say the relationship is 1, is it there? And then number 2, if it's there, is it a straight line or not? Is it linear or non-linear? Let's check it out. Hands up, ready? Go for it. Yeah, for the first one.
So it's a linear relation.
Why do you say that?
I say that because it's not perfectly straight line, but it's
It seems to follow a certain direction. Sure. So if I were to add a line of best fit, you would say something like that. And I kept on saying, have an equal amount of dots above and below the line, right? So this is just a guess. There's human error for sure, but you would say, yeah, that seems to be right. So confidently, I could say, you know what? I'm going to say this is linear. And let's continue on, Ellie. I'm going to ask you positive or negative. Yeah, you can also argue, take a look at the slope. Rise, run, rise, run. We're going in an upward staircase. So there you go. Do you think this is if you had to bet money, you got to put money down, would you bet that there is a strong relationship between age and height? Or it might be there, but it's not that strong of a relationship? Strong, yeah. The dots, another way you can say is the dots are very close to that line. You say it's strong. Let's move on to number 4. First off, is there a relationship in your opinion? Some people say yes, some people say no. Why do you say yes? Okay, sure. So as length gets bigger, area appears to get bigger. What other clues do you have to say, I think there is a relationship? Well, there must be something that made you think, you know what, I think there is something going on. I just don't know how to word it. The dots seem to be very close together. Every time I test it, every time I test data, it seems like they are going in a particular direction and they are close together. Yeah, but is the relationship linear? If I have an equal number of dots above and below, do you think that's a good fit? I'm going to say no. I would say that most of you might have thought there is a relationship, but it's more closer to that. It's getting faster and faster and faster and faster and faster. It's getting bigger, 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 bigger as we go. So yes, there is a relationship, but it is non-linear. I'm also going to say, again, look at the staircase. Yes, the staircase is changing, but it is still going in a positive direction. And I'm going to say the dots are pretty close to the line. It's a strong correlation. It's a strong relationship. Right? It's a strong connection, you can say. Which brings me to the next one. As the price increases, the amount of sales appears to decrease. I think there is a relationship. Do you think this is linear or not linear? Someone else? Take a guess. Not linear? So you would say, you know what? This fits. Okay. Other people have a different opinion. It could be non-linear. It could be. It could be that. That seems to fit too, right? So it's hard to say. So if it's hard to say, I'm going to say it could be both. I'm going to leave this blank. It's definitely negative though, because I'm going down. If you are not sure whether it's a straight line or not, is it a strong relationship or is it a weak relationship? The fact that you can't quite figure out whether it's straight line or it's a curved line tells you that it's not a strong connection between the two because it's ambiguous. You're not quite sure, but you do know that there is a relationship. So I'm going to say it's a weak relationship. Okay, so this one I can see both potentially being true. I need more data. Like for example, if more data showed me dots here and more data showed me dots here, I think you can confidently say, oh, it's more like this. But what if the data suggested that there were more here, like everywhere? Then maybe it's more of a straight line. I don't know. So we need more data if you want to be more sure. What about that last one, the second one? Someone else? Someone else? Think about it. Relationship, no relationship. And why? Okay, relationship or no relationship? Who says yes, relationship? Who says no relationship? Okay, people were just quiet. They didn't want to raise their hand. Okay, here's my argument. There actually is no relationship. This is a trick question. And because there's no relationship, you can't even figure out whether it's positive or negative. And therefore, obviously, there's no correlation because there's no relationship to talk about. The reason why it's hard to say is because there is temperature precipitation up here, temperature precipitation down here. There is temperature precipitation up here, but the same temperature and precipitation down here. It's everywhere. There's no pattern. And so it's really hard to tell. Is there a line going this way? I don't know. The line going this way is just as good. There's a line going horizontal. It seems to be just as good. It's really tough to tell. So clearly, I'm trying to paint a picture here. Today's lesson is about how to tell if it's strong correlations or not. And you use data analysis to figure that out. And this is another part of mathematics. There's an actual formula for this, and you learn this in grade 12. I really don't like this part. And so you let technology help you by using Microsoft Excel or Google spreadsheets and plugging into an equation, like a formula. Yes?
So, just saying, like, I can see there's a strong relationship because the dots are close together. Is that it?
Yes, absolutely. And we use the letter R, introducing the correlation coefficient. Makes you sound super smart, but it's actually very simple. Let's take a look at this exercise. Example number 2. Compare these two graphs. Which one do you think is a stronger relationship and why? So let me draw some lines of best fit. I think, again, human error, but I think that's not bad. And human error, that's not bad. Which one do you think is a stronger relationship and why? Yep, Marshall? No outliers. And be careful. Based on this, I think both of them, all the dots for both groups follow the trend. They're close in that they follow the trend. Yeah, it's a little off. That's not a bad thing because these dots still all head towards one direction. An outlier would be something that's up here, like in the top right corner of group A, right? And that is clearly, you know, when the trend is that as this gets bigger, this gets smaller. But here, as this gets bigger, the Y value became bigger. That would definitely be against the trend. But all these other dots, I wouldn't say that they're outliers per se. But why would you suggest group B has a stronger relationship? Anyone else have thoughts? Ethan, what about you? Essentially it. It's as simple as that. The data align in a linear relationship better, AKA, that's it. Long story short, if the points are closer to the line, then you have a stronger relationship. That's all it is. That seems simple enough. But the next question is, how the heck do we tell if it's closer or not? So yes, we have to give it a number. We have to give it a number. Here's the number. Introducing correlation coefficient with the letter R. Let's talk very quickly about what the number represents, and then we'll talk about what it actually means. Okay? Part one. If you have a positive relationship, like this one right here, a perfect positive relationship has an R value of 1. There is no 1.1. An R value of 1 means for every X, it's perfectly matching with the Y. In the same way, if there is a perfect negative relationship, we would call that R equals -1. But in this case, are those dots perfectly aligned with the line? No. So that's why this label says approximately -0.9. It's a little bit, it's not quite -1. So this is maximum correlation in the positive direction. This is maximum correlation in the negative direction. Everything else, all the other numbers, gives you an idea of whether it's decent or not so decent. Please note, in real life, a good positive relationship, if you have an R value of like 0.8 or an R value of like -0.8, that is good real life data, suggesting really good relationships. There's no such thing as R equals 1 or -1 in real life. If you do that, it's to the point where you're like, did you lie about your data? Like that's how intense an R value of 1 or -1 is. Okay? Take a look at some other examples. Look here. If this is real life data, even dots that are that far away from the line is still considered good. It gives you a new idea of how you wrote about your Barbie bungee. Some people are like, oh, it's off by like this much, so maybe it was an outlier. Not really. The data that everyone here had for the Barbie bungee was really good. So if you said, my data wasn't that good, it's actually not true. Your data was amazing. You just didn't know, right? So think about it that way. Here, it is a positive direction, isn't it? However, the R value is a 0.5, so it's not the best. I would suggest doing more data to make sure you are talking about the right one. Something like this, where the dots are scattered, the R value is a 0, like it's too hard. There's nothing, right? And then we have a negative. It's not that great. There's too many dots going all over the place. It's really hard to tell whether you see a relationship or not. So how do we let's first define what the R value is. Let's use this thing. Okay. This is what the R value is trying to show you. The R value is essentially trying to figure out how large is the area of these squares as you try to create perfect squares from the dot to the line. Your line of best fit is trying to make these squares as small as possible. So for example, let's pretend I had human error and I was like, hey, this is my line of best fit. Trust, okay? Humans make errors, this is the best I can do. Well, I will say, okay, let's make these squares with this line, right? Where one of the corners touches the dot and the other corner touches the line. Is that the smallest? Is that the best way you can minimize the area of the square? In other words, can you draw smaller squares if you change the line? Yes, right, I just did it. So that is a bad line of best fit. Instead, if I do something like this, the area of the squares becomes significantly smaller. So that would be a better line of best fit. That's exactly what we're supposed to do. But who's got time for that? Who's got time to draw a line and draw squares, measure the area of those squares using a ruler, adding them all up and being like, oh, that number area is bigger than this other line that I drew. No one's gonna do that. So we use things like Desmos and the computer will do all the squares for you in an instant and then figure out what the best line of best fit is. Well, that's why we learned the code, and I gave you the code here. All right. So let's first learn how to draw a line of best fit, okay, and figure out how Desmos can give you the R value. Remember, if an R value is 1, perfect correlation. If the R value is negative, perfect negative correlation. Yes.
I'm sorry, this is a silly question. But
for now, if you're doing it by hand, you have to eyeball it. Yes, and they'll give you a perfect line. So let's turn the page. If you have your computer open, amazing, go to desmos.com. If you do not, well, go to it, okay? All right, let me take a your TDSD encounter. All right, well, okay, well, we're gonna work together to figure this out. The homework that we have, I guess you can try it at home then. All right. Here we go. If you want to follow along with me so that you know how to use it. If you aren't following along with me, make sure you take good notes because you will need this for Friday. Okay. Going to, oops. Why is it bad gateway?
It does that. Yes.
Are you serious? Internal means it's on their side. Timeout, yeah. No, Desmos. Why, Desmos? Dang. Give me a sec. Yeah, it's either they crashed or something. All right, well, it is what it is. Maybe by the second example will be good, but we're gonna have to wait it out. Well, that sucks. That ruins everything. Okay. So what I wanted everyone to do was go to Desmos, and when you go to the calculator for Desmos, on the top right, you will see a plus sign. Would you take a look at the picture that I had earlier? Right, in our handout, there's a little screenshot. If you click on that plus, there's a small menu that pops out, and one of the menus says add a table of values, and it looks like this.
How do you get into that?
Just type in desmos.com, but right now the server is down, I think. Okay, or their website is down. So just bear with me. From here, when you plug that in, on the right column, there's going to be 1, 2, 3. It will insert a table on this column. I think you might remember it from your previous uses. So it has an X1 and a Y1, and that's very important. Under X1, you are supposed to plug in 1357. And the Y values that partner with it is 1367. And that will automatically have generated a 0.11, a 0.33, a 0.56, and then 77. So basically it's a straight line, but one of the dots is slightly off. 5.6, yeah, it's a 5.6, okay? From there, what's interesting is, as long as you specify, this is important, everyone, as long as you tell the computer to use X1, it will try to use all the numbers here. And if you tell the computer to use Y1, it will try to use all the numbers here. So in the next line that says 2, if you type in the code CORR open bracket, it automatically knows it's trying to use a formula for correlation. And you say, and the computer's like, okay, what do you want me to make a correlation of? Type in X1. And if you type in just X1, the computer will automatically put that as a subscript, as a mini one. Yes. Thank you, Warren. It's working? Yay. My life. Warren, I love you. Here we go. Again, how we do this? So much faster. With the plus sign, there's a table. Click on the table. You get a table. 1357. If you just enter it, it automatically goes to the next line. So 1, enter, 3, enter, 5, enter, and 7. Oh, it automatically fills for you. I don't want 9. Notice about the X1 and the Y1? Click on the Y value and you're doing 1367. Ta-da! Just as I said, they put in the dots for you. From here, go to the next line. So you can't see it here because technology, but that is box number 1. This is box number 2. In box number 2, just click it. You are going to type in the formula CORR, or just COR, open bracket, CORR, open bracket, X1, and it automatically becomes a subscript, comma, Y1, close bracket. Ta-da! What is that? It means the correlation coefficient. That sounds like a kid rhyme, okay? Correlation coefficient R is 0.98. In other words, if you have a line of best fit, would you say it's a decent relationship? Yeah. It's a really strong positive relationship. So essentially, that's what I need you to do. So go to the next page. We're going to do this example together. I'm going to give you 5 minutes, erase all of this, put in the X1 being discount, put in Y1 being increase in number of umbrellas sold, and then calculate the correlation coefficient. Go for it. And I'll do that with you while you get through this. So we've got Pardon? Yeah, yeah. So, okay, we got look at the sheet. Yep. Going back to the sheet, take a look. It says enter the table and then plug in the expression core x1, y1, x1 comma y1. Let's take a look.
How is the technology solved?
From here, again, go to the next line. It's super powerful in that as long as you refer to x1, it automatically knows to look at this chart. Look, if I just plugged in x1, it's like, hey, I have 9 items on that list, right? So correlation of what? Of x1 with y1. Ta-da! What is my R value?
Oh, so you just put that in to get it, like, dot. If you were doing those equation with no computer software, would you still use that for things?
No, it depends on the program. For example, Microsoft Excel will have a different formula, right? This is just for Desmos. So this is it. And so I am going to go back to my sheet and say my R value is 0.899. Yeah. It's a very strong correlation because it's close to 1, right? Very, very strong. What is the strength and direction of the relationship in words? So you can say something like, it is a strong, positive correlation. So you add both adjectives into a single sentence. Okay? Any questions so far? These are just basic instructions I'm giving you for our assignment on Friday. What is it? Look at the previous sheet, the big title in the back of the first page. The correlation coefficient.
I didn't know it was good for something like on its own, like if I had a bigger word, just R.
Nope, just R. And you'll see when you get to grade 12, there's a little r and there's a capital R that means something else. Like it's, yeah, so brace yourselves. Yes?
How do you make the line of best fit of this?
You'll see. You'll see. It's in the last page. I want to get there. Ready? Outliers with R. Here is why I love technology for data management or data analysis. If there is an outlier, you would have to calculate everything by hand again. But using technology, it'll just reset everything after you erase. So let's go through this again. Weekly rainfall as your X1, number of umbrellas sold as your Y1. Plot it and see if there is a outlier, and we'll figure stuff out together. Here we go. I need a table. X1 is 38, 24, 15, 10, 6, oops, 10, 6, 6, 3, 3, 0. And then 16, 10, 4, 13, 4, 35, 4, 1, 0. Okay, what do you think? seeing this as your scatter plot, is there a trend? Not right now, but what if I said this was missing? Oh, what if I said this was missing? No relation. What if I said this was missing? Still no relation. What if I said this was missing? Still no relationship. Once this is gone, all of a sudden we see a relationship. And so maybe that would be my outlier. Okay. So is there an outlier and what is it? I'm going to say the outlier appears to be 635. I'm doing it in brackets. 6, 35. So I am going to determine the correlation coefficient with the outlier and then determine the correlation coefficient without the outlier. And we'll talk about it. Ready? Okay. So everyone with me? Look up here. CORR, RR, X1, comma, Y1. Whoa. Is that a strong relationship? How would you describe 0.25 as your correlation coefficient? Is it positive? A positive number? Is it a positive? Yes. Is it strong? No. So this is a weak positive correlation. The closer it is to 1, the stronger it is. Yeah, you got to keep up. Here. So let's try to erase what we identified as our correlation, as our outlier. So I'm going to erase the 35 and the 6. Oh, I need to actually like erase all of this. Oh, perfect. And bam, from a 0.25, it became a 0.82. It became absolutely a strong positive just because we got rid of 1. That means it has to be an outlier, right? So determine the correlation coefficient. So that R was about 0.25. And I removed it. The R became 0.82. Explain the change in R when you remove the outlier. Well, I could say, when the outlier was removed, oops, I will say the R value, the R became significantly closer to 1, which is strong positive. It literally jumped from almost no relationship to a super strong positive. So you know that's probably like most likely to be an outlier. So the question, why is R helpful in identifying outliers? Why is this helpful compared to what you had before? What was the other way we calculated outliers yesterday? Oh, it's the CORR. We'll get there. We'll get there. We're almost there. We're almost there. Okay, that's the next thing. We're doing the line of best as the next thing. Okay. Michael, but erase this again and try typing it again. There might be a format thing where you were playing around or something. Okay. So how is this helpful? Well, I'm going to say something like, right? Another way I could say it is automated. Another way you could say it is What else could you say? There's so many things you could say, but just to make sure, just to save ourselves some time, right? It's easier to see if a number compares or is getting closer to a 1 versus not, right? Using an IQR times 1.5 and seeing if the number is bigger than the number I got or smaller than the number I got with the box and whiskers, it's still a lot of work, well, relatively speaking. Compared to this, putting in the data and asking to see, is there a relationship using the, using the squares and stuff? Nice, it's easy, right? So there it is. Lastly, so now that we know there's a correlation, if there is a correlation, it would be nice if I could get a line of best fit, like the equation y equals mx plus b. So how can we get the computer to help us with that? Going back to Desmos, right? Go to the next page. We're going to learn how to draw a line of best fit. Okay, this one, I need you to actually draw something in your equation. Okay, let me plug this in. I need you to draw something on your handout, so bear with me. In your handout, Ryan, hey, everyone with me? Maddie, okay. Michael, everyone? On your sheet, I would like you to draw your best line of best fit going through the y-axis. So take a ruler or any kind of straight edge, and with human error, see if you can draw your best line of best fit. Something like that, maybe. What do you think? Is mine not bad? Remember, I'm trying to get the space between the dots and the lines as small as possible. So you're not going to get a perfect situation, but I think this isn't bad. So everyone got it? Can I move on? Okay. Select 2 points on the line of best fit and calculate n. Exactly what you were supposed to do with Barbie Bungee. So I am going to use, what's a nice point? This looks like a nice point. I'm going to use 6,170. I am also going to use, this doesn't look too bad, 3,100. My m is remember, your numbers might be a little different than mine. Okay? So this gives me 70 over 3. Well, I could leave it as 70 over 3, or for your sake, just to have a better understanding, this is about 23.3 repeating. But I'm going to leave it as a fraction. Now I need your help. Based on my curve, or based on my line of best fit, what's my y-intercept? Look up here. What's my y-intercept? About 45? No. This is 40. Oh, 25. Yeah, maybe. Wait. 10, 20, 30, 40, 50. I think it's more closer to a 30 than a 25. Let's do 30. So my final equation is about y equals 70 over 3x plus 30. Okay. So this is my best guess using human error. Everyone with me? This is important. This is the extent of my human abilities because I'm eyeballing. Yeah? Eyeballing. With me? I'm going to take that same data, these 7 dots, and I'm going to put it into Desmos. So if you go to the next page, the number of rubber bands is 1 and the height is 50. Here we go. So going back to Desmos, I'm going to leave my equation, my human equation here, so that I can compare it later. Let's plug this in. 1, 2, 3, 4, 5, 6, 7 bands. 50, 68, 85, 111, 130, 148, and 170. Okay, zoom out, zoom out, zoom out. Oh, that doesn't look very pretty. Let's see if I could fix it. Nope, still doesn't look pretty. I'm going to change my axes. People here, you might want to do this too, so pay attention. My y-axis is nice, but I want to start here and I want to finish here so I can get my dots to sort of spread out a little bit. So I'm going to get my x-axis and say, hey, I want my x-axis to start at -10. And I want my x-axis to finish around 20. 20. And then it will stretch out the x-axis from -10 to 2040. Not bad, right? And all of a sudden we see a nice relationship. Okay. Maybe, you know what? I'm going to stretch it a little bit more. I'm going to go to 10. And from -1. Look at that. Sweet. Is everyone with me? Okay. Nate, here is my instruction. You ready for the line of regression? Line of regression is basically another way of saying line of best fit, a linear regression. Just say it with, just whisper it under your breath with me, okay? Linear regression. Here's another one that you might see. Quadratic regression. Exponential regression. These are things that you might see in the future, but the word regression means line or curve of best fit. So there's your big smart word for today. How do we do it? Well, you know that the line of best fit should be y equals mx plus b, right? But what? It's not just any y. It's not just any x. What's my y here? It's all of this. So you tell the computer, my y is actually y1. Okay. So y is actually y1. X is actually x1. And you don't say it's equal. You say it's around x1 equals y1. So instead of equal sign, I want you to put in a tilde. A tilde is one of these on your keyboard. The squiggly. The computer registers that as approximately. Where it is on a typical keyboard, it's this one right here. So you have to press shift up left corner. Yes, so shift that and it gives you a tilde. Why is A called A? I don't know. Whoever invented this maybe had a last name tilde. I don't know. Everyone wants to leave a legacy on this earth, right? So there it is. If you say y1 is approximately slope times x1 times a b, it'll be like, hey, you have, everyone here? Rehan, and boys, just one second. You have a correlation coefficient of almost 1. That's immaculate. Real life data will never get you 1. So 0.999 is almost perfection. Okay, next. So in other words, it's a very, very strong positive relationship. What's the slope? About 20. And what's the b? 28.1. What was my equation? My human-made equation was 23.3 plus 30. It was pretty close, and it was pretty close. Was it perfect? No, and that's where human error comes in. But with the advance of technology, we actually don't need to do all the nitty-gritty data management related calculation. The computer will do it for you because the computer already has the formula. It's doing all the calculations for you for every single point, creating a square, creating a little square for every single point, and trying to minimize the size of that square as possible. It did a pretty good job, don't you think? Right? And any change in that line slope makes those squares bigger. And so it's like, this is the best one I got. All praise technology, I guess. Okay, so removing any outliers, go back to your sheet. What is my equation? My equation is y is equal to, what was the slope? 20 point. What was the slope again? 20.1786. 1786x plus, and what was my y-intercept? 28 point, I heard a mumble. 1429. 1429. Question, could you compare your equation determined by hand, which is this one right here, and that is determined with the help of Desmos. How do your two equations compare? They are close, but human error makes my equation slightly off of a perfect line of best fit. You know what? Instead of perfect line of best fit, let's call it line of perfect fit. Sure. There. M. It says M. Yeah. Yeah. So the computer will find you the slope and y-intercept. And this is something that you can probably take with you even into grade 10 when we stop doing line of best fit and you start doing some curves as well. Okay? Your task for today essentially is to familiarize yourself with this stuff. Okay? There is some homework and there are some exercises I'd like you to do with Desmos. Tomorrow, in preparation for your problem set, or sorry, in preparation for your assignment, I'm going to be giving you a kind of problem set that gets you to use Desmos. So if you feel comfortable bringing your Chromebook tomorrow as well, do so, because you will most likely need it for Friday as well. Just bring it for the rest of the day just in case. Okay, we'll finish this off tomorrow. It's basically an exercise to make sure you know how to do all the different aspects of Desmos. And that essentially brings us to the end of our data analysis unit. Questions and questions?
We have our makeup test tomorrow, right?
Pardon?
Our makeup test
Correct.
tomorrow. Is that lunch or is it just?
In class. I'll give you the 50 minutes plus whatever. The Tilda? Yeah. If you're on a Chromebook, correct me if I'm wrong, is the Tilda on the Chromebook?
Yeah.
Oh, it's right there. Okay. And that's it. I'm going to pause this or stop this video here and we'll talk.